Welcome back. In this segment, we're going to be studying the topic of confidence intervals. We study this topic when we're trying to estimate a parameter. Remember from Chapter 1, a parameter is some value of the population that we're interested in finding out. Well, we're trying to find out what the value of a parameter is for a population. Now, one way to find it is to survey every single member of that population. Most often, it's not practical to do that. So let's say I was interested in the proportion of students who have cell phones. One thing we could do if we wanted to go and find out the exact proportion is to survey every single student on campus and ask, do you have a cell phone? And the student would answer yes or no. And we would be able to find the proportion. Well, it's not very realistic. So instead, we do a survey. Well, when I do a survey, I have to decide how I'm going to survey and also what my sample size will be. Suppose I decide that I will just survey one student. I'll ask the next person who comes into the classroom, do you have a cell phone? And if the next person says yes, then I will have completed my survey and I will know that 100% of students have cell phones. Well, let's say the person said no. Then I would know that 0% of students have cell phones. Well, you may already realize this is a really poor way to take a sample. Convenient sampling with a sample size of 1. Well, instead, what I might decide is I might go to the campus center and stand on the area where the fountain is and just shout out, who has a cell phone? And the number of people who raise their hands, yes, I have a cell phone, I'll count those people. And the people who don't, or who say, no, not me, I'll count those people. Then I'll have a slightly better estimate. Well, this segment deals with how to find some sort of an interval for the estimate that we're trying to come up with. All right, now, we often see confidence intervals in the newspaper, on television, in the media. Anytime a politician is running for election, we read about polls, a certain percent that approve the politician's platform or planning to vote for the politician. This involves taking a poll and coming up with a point estimate. A point estimate is the value that's determined from taking the survey. This would be the statistics, such as X bar if it were an average, or P hat for a proportion. And then in the newspaper, we often read with a margin of error of plus or minus. This margin of error is what's called our error bound. And we're going to be determining how to calculate the error bound in this chapter. Well, here are some of the questions and some of the reasons we would want to find a confidence interval. First off, we don't know what the population average or proportion is. And in another course, we'll be studying what the standard deviation is. That will be another one. Also, we'll see up here that I have that what we're looking for is the estimate of the mean or the proportion. So the questions that we need to ask ourselves are, how many do we want to survey? What to do? We need to do the survey. How many should we survey? Why not survey the entire population? Well, we know that that would be very unrealistic. Why not survey one person or one object? Well, we just saw that that gives us inaccurate results also. And the confidence interval will give us a way of estimating the true value of the parameter. And so this is why we're going to do this. Now let's look at a proportion first. From the binomial distribution, one of the items that we discovered, hopefully you discovered this, was that when n got to be large, we could approximate the binomial distribution by using a normal distribution. If you graphed any of your data that followed a binomial distribution, what you saw is that the shape was approximately bell-shaped. Well, the binomial is discrete. We're counting, but yet the shape looked approximately bell-shaped, although made out of histograms. The mean of a binomial is n times p, and the standard deviation is the square root. I hope you can see that this is a square root sign. The square root, that's under square root of npq. That was the variance of the binomial distribution. And if x followed a binomial, we would say it's approximately normal. Now we're going to make another random variable called p hat. And p hat is the estimated proportion. P hat is equal to taking our random variable x divided by n. And so our normal distribution now, that mean, if each value were divided by n, the mean would be divided by n. And the variance, actually, we've seen before, is divided by n squared. And so we have the distribution for p hat is approximately normally distributed, centered at p, with a standard deviation of the square root of pq over n. So let's look at an example. Let's say we wanted to do a survey. And we did a survey, and I wanted to find out the proportion of students who had cell phones. And so I do this survey, and I'm going to ask students, do you have a cell phone? Well, I've learned my lesson. I don't want to just ask one student. So maybe I ask 100 students. So my x, what I'm counting, is the number of students with cell phones. And let's say I collect the data, and I find out that 44 of the students out of 150 have cell phones. And so now my point estimate would be p hat. This is a lowercase. I know it's very difficult to tell with the letter p and the letter x, but capital X is the random variable, uppercase. Lower x is the data that we're collecting. Lowercase p hat would be the data also. So this would be equal to 44 out of, or divided by, 150. And this is our point estimate. So this is the value that we get from collecting our data. Now what we need to find out is what will be the margin of error that we have. And before we decide on the margin of error, we have to decide a few other things. One of the things that we need to decide is how confident we want to be. And that's called our confidence level, how confident we want to be. That, and what we're confident about, is that our interval contains the true value of the parameter. So we're going to build an interval, and we have to decide how confident we want to be that this interval from the lower value to the upper value contains the true population proportion for the proportion of students who have cellular phones. The interval, CI, is abbreviated confidence interval, and this is the interval that we're actually building. It's an interval, so it will go from a lower value to an upper value. Now we're going to build a 95% confidence interval for this example. 95% is the most common that's used in industry. And that's the same for when we get to Chapter 9 for hypothesis testing. 95% is the most common. Legal cases use a 95% in most cases. Medicine uses 95% for most cases. If you see published reports on polls in the newspaper, these are using a 95% confidence level. All right, so let's see what that means now. If we have our confidence level as 0.95, we're letting alpha, this is lowercase alpha, be equal to our, we're going to call it our unconfidence, how not confident we are. So if we're 95% confident, that means we're 5% not confident. And alpha over 2, which is the area that we'll see in just a minute in each tail, is going to be 0.025. That's how much area we have in each tail. Now, we don't need to get this off the calculator, but I will show you how to do it in just a minute. Our error bound for the proportion is the amount of area, or the amount that we're going to add to the point estimate and subtract from the point estimate to come up with our interval. And if we want to find the error bound, we have our error bound. The error bound is equal to the z-score, which is, in this case, 1.96. Again, I'm going to show you how to find that, times the square root of pq over n. So let's go over a little bit of this on coming up with this. What we know from standardizing values is that lowercase z-score is equal to what we get from our data. This is a lowercase, minus p, the actual proportion, divided by the square root of p times q over n. Now in this case, what we know is the value, the estimated value, and we know how many we surveyed. Q, if you remember, is 1 minus p. So the probability of success is p. Q is equal to the probability of failure. Well, if we cross-multiply, so we take the denominator and we multiply, we're going to get z times the square root of p times q over n is equal to p hat minus p. What this is our error bound. So this is our error bound, which means that this is our error bound. So our error bound for proportion is equal to the z-score for a certain amount of area in the tail times the standard deviation. All right, let's go back to this example that I was just dealing with. In this example, we had n was equal to 150 students. Lowercase x was equal to 44. So lowercase p hat is equal to 44 over 150. And what we want to do now is we want to build the confidence interval. And so if we start, we can start by graphing this. When we start to graph this, we're looking for, we put our point estimate right here. And we're looking for two endpoints. And these endpoints, the lower limit and the upper limit, will be built such that we have 95% of the area in between them. So we have 95% of the area in between them. That's why I divided the 5% by 2. We have 5% left over. So 0.95 is equal to 1 minus alpha. 5% left over, and then 0.05 divided by 2 is the amount of area in here, and also the amount of area in here. So we have this 5% divided by 2 left over in each tail. Now, what we're looking for is this value and this value. We're going to do it once by hand, still using the calculator even though it's by hand, and then we'll do it on the calculator from then on in. By hand, we have that the error bound for proportion is equal to the z-score we need times the square root of pq over n. Now what happens is, because we don't know the actual proportion, we're going to put a p hat and a q hat here and use our estimates. Where the z-score comes in, I'll show you right now how to get this on your calculator. Where the z-score comes in is we need to find the area in the tail. So I'm going to go down to the inverse normal, and we're looking for 0.025 area in our tail for a standard normal, which means that the mean is 0 and the standard deviation is 1, because that's for z, standard normal. We get negative 1.96. And so we have negative 1.96 on our graph, and then the opposite one will be 1.96. So we have I'm going to just use the positive of it because we add and subtract when we're taking the margin of error, times 44 over 150 times 106, because 106 plus 44 gives us 150. And I better make the square root bigger, divided by 150. And this is the amount that we would add and subtract to the 44 over 150 to get the bottom value right here and the top value. So we take 44 divided by 150, which is 0.2933. So we have, this is 0.2933. And we'll have 0.2933 minus this value. And here we have 0.2933 plus the value, the error bound p. This will give us our confidence interval. What we'll say is that we're 95% confident that the true proportion of students who have cell phones is somewhere between this lower value and the upper value. Let me show you how to do it on the calculator now. Okay, we're going to go in here, and we're going to go into the tests. So we go into Stat, Tests, and we want to go down for the intervals. And here we have at A, one proportion. We're doing a proportion, and we need a z interval. It's normally distributed. And so our x was 44 out of 150. Our confidence level is 0.95. Whoops. And now we're going to go down and calculate. And what we find out is, first off, p hat, we read that, p with a little hat over it as p hat, equals 0.2933. We know that. Our lower bound is 0.2205, and our upper bound is 0.3662. The error bound is half of the distance. So if we wanted to find the error bound, we'd do 0.3662 minus 0.2933, and we get 0.0729. So we are 95% confident that the true proportion of students is from what the lower bound is to the upper bound. Now, if we look at this formula right here, here's the formula. If we were to survey more students, instead of 150, let's say we surveyed 1,500, you would have a bigger number in the denominator. With a larger number in the denominator, think about what will happen to the overall fraction. Will the overall fraction get larger or smaller? And by getting larger or smaller, what happens to the error bound? Hopefully you've thought and you say, well, if n gets bigger, then what happens is my fraction gets smaller, so the error bound gets smaller. And if the error bound gets smaller, I'm adding and subtracting less than before, and so my interval will close in. So one way to get more accurate is to survey more people. Well, this is confidence intervals for proportions. Now let's work on some confidence intervals for averages. Many years back, there was a man named William Gossett, and he invented a way for dealing with confidence intervals when the population standard deviation was not known. And this is confidence intervals for averages. And in his particular case, he was looking for averages for small sample sizes when the confidence interval needed to be determined, and we were looking for average, and we did not know the population standard deviation. Now, this is the most common case. If you don't know the population average, you most likely don't know the standard deviation, because the standard deviation formula comes from the average. So William Gossett invented a distribution called the student t distribution. And the student t distribution deals with cases where the population standard deviation is unknown. But now, here's the sort of confusing part. The underlying population of x, of the individual values, is assumed to follow a bell-shaped distribution. You can't know that unless the problem states that, which means that a statistician has checked out that information. The test to determine if the distribution does follow a bell shape is past this chapter. So you'll be able to eventually know that. So again, we're going to deal with what's called the student t distribution when we have a distribution that we're trying to find the information about the population average. We do not know the population average, or we wouldn't be trying to find the information. We do not know the population standard deviation, and so what we use is the sample standard deviation to try to estimate the population standard deviation. So let me put up some information on here. Okay. The student t distribution is used when the population variance and standard deviation are unknown. We're going to estimate the population standard deviation from the sample standard deviation, and the underlying population is assumed to be normal. To use this, to use the student t, what we do is we're going to estimate the population standard deviation. Remember, the population standard deviation is lowercase sigma. We're going to estimate it by s. We have a new term that comes in, and you can read about this in the text, called the degrees of freedom. And the degrees of freedom are equal to the number that you survey minus 1. And we have a new random variable. Our test statistic is our value that we have minus the sample mean. And since we don't know the population mean, we use the sample mean in its place, divided by S over the square root of n. This is similar to the z-score. And the notation, which is normally used, I'll zoom right here on this. The notation that we normally use is a student t. We put in the degrees of freedom and the area in the tail. So let's do an example that we have with this one. Let's say we want to find a 95% confidence interval. So 95% confidence interval for the average speed, let's see, a BMW Z3 owner drives at on the freeway. Insurance companies might be interested in this. If they're trying to decide on insurance rates, they take into account the color of a car, the make of a car when they decide on your individual insurance rate, and the age of the driver, along with some other items. But we want to find the 95% confidence interval. So we do a survey, and here's our survey results. Do a survey, and we find that the sample mean is equal to 74, and the standard deviation for the sample is equal to, let's say, 18. And we do this survey from surveying maybe 25 people. We survey 25 people. We have a sample mean of 74 and a sample standard deviation of 18. And now we want to build our 95% confidence interval. So on our graph, we're going to have the graph here. We're centered at 74. And we want to have 95% confidence interval. When I go to calculate this now, I want the error bound for a mean, not the error bound for a proportion. And you can read in the text the derivation. The error bound for the mean now will be the student t-score times the sample standard deviation over the square root of n, which is how many you're averaging together. Now, I'm not going to do this one by hand because we don't have time, but you can do it by hand and then go on and do it by the calculator. And let's see what we come up with. We're going to go down to the student t interval, right here, t interval. By the way, be sure you read the difference between the z interval and the t. The z, we use the normal distribution when we know the population standard deviation. When we don't know the population standard deviation, regardless of the sample size, we use the student t. So the difference between these two is the normal can be used when sigma, lowercase sigma, is known, but the student t is used when we don't know lowercase sigma. And so we're going to do the student t interval. The calculator in this program asks us, do we want to enter our data or stats? We're going to do the stats. The sample mean was 74. The standard deviation was 18. N is 25, and we want a 95% confidence interval. Well, let's see what happens as this is calculating. It tells us that the 95% confidence interval is from 66.57 to 81.43. So I'm going to just mark that on the graph. 66.57 up to 81.43. This tells me that we're 95% confident that the true average speed of BMW Z3 owners on the freeway is between 66.57 and 81.43. This doesn't have anything or any, it's not saying anything about individual speeds. It's only talking about the average speed. Well, let's look back at this graph again and see what happens if we want to change our confidence level. Let's say we want to be more than 95% confident. We want to be 99% confident. Well, now remember the area under the curve, the total area is 1. So we need to push out so that we have 99% of the area shaded in. So now we're going from here to here. We would expect then the 66 to become lower and the 81 to become higher. Let's do that. And this will be the last thing we do on this section here. We're going to go back into the T, and all I'm going to change is the confidence level. And hopefully what we'll see now is that our values change. We still have 74, 18, and 25 because that's what we entered. But now if we wanted to be more confident, we went to 63.93 and 84.07. So to become more confident, this value becomes smaller and this one becomes larger. And that's because we want more area under the curve. If we wanted to be less confident, we could go in and we would get a smaller error bound. More confident, we go out, we get a larger error bound. Well, that's the summary for confidence intervals. We did a proportion and we did the average for when we don't know the sample standard, or when we don't know the population standard deviation. In the next chapter, we're going to continue on with this information and start trying to come up with hypothesis testing or testing about values based on our data. That's it for now.